Have you ever wondered which metal element discovered by humanity is the hardest and the most difficult to melt? The answer is the metal we're exploring today, tungsten. Tungsten isn't just physically extreme in its hardness and heat resistance, it also has chemically unique properties. In fact, even the name tungsten was given because of its distinctive characteristics. So where does the name tungsten come from? And if it starts with T, why is its chemical symbol W? But the story doesn't stop at its name. Where is tungsten actually used in our world? In today's video, I'll walk you through the scientific and engineering appeal of tungsten, the most powerful metal on Earth. Before we dive in, make sure to hit that subscribe button down in the corner. Now, with that out of the way, let's jump right into it. Before we get into the details, let's talk about the story behind the name tungsten. The word actually comes from Swedish, where tung means heavy and sten means stone. So, quite literally, tungsten translates to heavy stone. It's a fitting name because minerals containing tungsten are remarkably dense and heavy. Interestingly, it wasn't always the name of the element itself. Originally, it was a general term for any mineral that contained this unusually heavy material. But that changed in 1781. Swedish chemist Carl Wilhelm Scheele discovered a new compound in a mineral called scheelite. He identified it as tungsten trioxide. Scheele realized that this heavy stone wasn't just an ordinary mineral, it contained a distinct and important compound. From that moment, the name tungsten truly began to make its mark on the scientific world. Taking that discovery a step further, just 2 years later, in 1783, the Spanish brothers Juan José and Fausto El Huya reached a major milestone. They succeeded in isolating pure metallic tungsten from tungstic acid, a critical discovery that confirmed tungsten was a distinct metallic element in its own right. The El Huya brothers then adopted the name tungsten from the mineral, establishing it as the official name of the metal we know today. Now here's an interesting question. If the element is called tungsten, why is its chemical symbol W instead of T? To find the answer, we have to go all the way back to medieval Europe. At the time, tin was one of the most vital metals, essential for making bronze for weapons, tools, and countless everyday objects. But as miners extracted tin ore, they often found a strange mineral mixed in with it. The problem was that this mineral interfered with the smelting process. When miners tried to extract tin, it didn't just sit there harmlessly. It reacted during heating, reduced the amount of usable tin, and produced unwanted slag. Instead of helping, it made the whole process more difficult. To the miners, it wasn't just some annoying rock. It literally cost them valuable tin, so they gave it a rather hostile name, describing it as a wolf devouring the tin. In German, Wolf means wolf, and Ram refers to a frothy or creamy residue. Put them together, and you get wolfram. That name is where the chemical symbol W comes from. While element symbols are usually assigned based on standardized rules, W was chosen for tungsten because the name was already deeply rooted in the German-speaking scientific community. This also serves as a reminder of the significant influence German scientists had in the early development of modern chemistry. Now let's turn our attention to the properties of tungsten. What makes it so remarkable? True to its name, meaning heavy stone, tungsten is considered one of the hardest pure metals. When we talk about hardness, we're referring to how well a material resists scratching or permanent surface damage. Tungsten's Vickers hardness is around 3.4 gigapascals, placing it among the highest of all pure metals. To put that into perspective, the stainless steel we commonly use in kitchenware typically falls in the range of 150 to 300 megapascals. That massive gap gives you a sense of just how tough tungsten really is. But hardness isn't the whole story. Its tensile strength is just as impressive. While many metals measure in the hundreds of megapascals, tungsten can exceed 1 gigapascal, allowing it to withstand enormous mechanical stress. Compared to pure iron, it can be roughly 3 to 5 times stronger under similar conditions. Yet, there's even more to it. Tungsten is also incredibly dense. In fact, among all known metals, tungsten ranks about 5th in density, behind osmium, iridium, platinum, and gold. And then there's the melting point. Tungsten doesn't melt until it reaches a staggering 3,422 degrees Celsius. For perspective, titanium melts at 1,668 degrees and iron at 1,538 degrees. That massive contrast alone makes it clear just how extreme tungsten's properties truly are. So, what's the secret behind tungsten's extraordinary properties? It comes down to its atomic structure and the way its atoms bond. Tungsten has an atomic number of 74, which means each atom contains 74 protons and 74 electrons. What makes it especially interesting is that some of those electrons aren't locked to a single atom. Instead, they move freely throughout the entire metal. These free electrons travel between positively charged atomic cores, effectively binding the atoms together. This is what we call metallic bonding, and it's how all metals are held together. What sets tungsten apart is the strength of that bonding. In tungsten, the density of the free electrons involved in bonding is relatively high, leading to a very large metallic bonding energy between atoms. Put simply, it takes an enormous amount of energy to pull tungsten atoms apart. That's why tungsten has such exceptional strength and such an unusually high melting point compared to most other metals. So where then is tungsten actually used? One of the most prominent applications of tungsten's exceptional physical properties is in cutting tools. In particular, tungsten carbide, a compound made from tungsten and carbon, is widely used as a tool material. Tungsten carbide is incredibly hard, far harder than most common alloys, and it resists wear extremely well. That's why it's used in high-speed cutting applications, from drill bits and saw blades to milling cutters, lathe tools, rock drilling bits, and even excavator teeth. But where it truly shines is at extreme temperatures. During high-speed cutting, friction can drive tool temperatures to intense levels. Most metals begin to soften under that kind of heat, losing their hardness and cutting ability. Tungsten carbide, however, does not. It holds its edge even under extreme thermal stress. One application that pushes tungsten's thermal stability even further is its use in filaments that produce light and heat. You've probably seen a traditional incandescent bulb. The thin wire inside that glows and produces light is made of tungsten. When current flows through the bulb, the filament heats up rapidly and begins to glow. But this raises a critical question: just how extreme does the temperature get? The answer is far beyond what most people imagine. In a 100-watt bulb, the filament can reach around 2,800 degrees Celsius. In a 60-watt bulb, it climbs to roughly 2,500 degrees. To emit visible light efficiently, the filament must operate somewhere between about 2,500 and 3,000 degrees Celsius. At temperatures like that, most metals would already have melted. Tungsten doesn't begin to melt until about 3,422 degrees Celsius, which is why it works so well as a filament material. Surprisingly, tungsten filament halogen bulbs haven't disappeared. Even though most household lighting has shifted to LEDs, they're still lighting up car headlights, film sets, and certain medical devices. Tungsten filaments also remain essential in high-temperature systems, from electric furnaces to specialized scientific and industrial equipment. As mentioned earlier, tungsten is an exceptionally dense metal. Combined with its high hardness and outstanding thermal stability, these properties make it the ultimate material for modern warfare. One prominent example is its use in high-density penetrators such as APFSDS rounds, often referred to as tank killers. These projectiles are designed to pierce the thick armor of tanks, armored vehicles, and fortified structures. At the heart of this penetrator lies a solid tungsten core. Because tungsten packs a tremendous amount of mass into a relatively small volume while retaining its strength even at high temperatures, it is exceptionally effective at penetrating heavy armor. Tungsten is also used to reinforce the warheads of so-called bunker buster munitions, which are intended to destroy hardened underground structures. When a dense projectile traveling at high velocity strikes its target, its kinetic energy is transferred with tremendous efficiency, significantly increasing both penetration depth and destructive capability. Beyond these applications, tungsten is used in missiles, rockets, and heat-resistant components in high-speed aircraft, where materials must withstand extreme mechanical and thermal stresses. The final application we'll explore is tungsten's role in radiation shielding. What makes radiation so dangerous is its ability to pass through solid materials and disrupt their internal structure. But not all materials respond the same way. Elements with very high density and high atomic numbers are far more effective at absorbing or attenuating radiation. That's where tungsten comes in. With both an exceptionally high density and a large atomic number, tungsten is highly effective as a shielding material. So where do we actually see this in practice? When people hear the word radiation, they often picture nuclear power plants. And yes, tungsten is used there for shielding, but its role extends well beyond nuclear facilities. In medicine, for instance, CT scanners generate radiation, and tungsten components help contain and control it. Tungsten is also used in protective capsules that safely store and handle medical radioisotopes. For decades, lead dominated radiation shielding, but once its toxicity became impossible to ignore, engineers began searching for something better. That's where tungsten stepped in. Tungsten is far denser than lead, which means you can achieve the same level of protection with significantly less material. That translates directly into lighter, more compact shielding systems without sacrificing performance. So far, we've looked at just how widely tungsten is used. What's your impression? It shows up in so many different fields that it almost feels indispensable, but like any material, it isn't without its drawbacks. Tungsten has its downsides too. One major concern is the environmental impact. In nature, tungsten doesn't exist in pure form. It's found in minerals, chemically bound to other elements. Extracting pure tungsten requires multiple processing steps, many of which involve strong acids such as sulfuric and hydrochloric acid. This can produce acidic wastewater, toxic byproducts, and heavy metal residues during refining, all of which can pose environmental risks if not carefully managed. Carbon emissions are another concern. Producing tungsten typically involves a final reduction step, where oxygen is removed from tungsten oxide using carbon or hydrogen. When carbon is used, the process releases greenhouse gases such as carbon dioxide and carbon monoxide. That means tungsten production can work against the global push toward carbon neutrality. Beyond environmental concerns, there's also the question of resource availability. Tungsten is relatively rare in the Earth's crust, averaging about 1.25 parts per million, or roughly 0.000125%. At current consumption rates, economically recoverable reserves could last for about a century, but those estimates depend heavily on future demand, new discoveries, and advances in extraction technology. Recycling certainly helps, but tungsten isn't easy to reclaim. Its chemical stability and extremely high melting point make the process energy-intensive and technically complex, especially when it's embedded in advanced alloys or carbide materials. In fact, tungsten is regarded as a strategic metal in many countries because of its essential role in industry, defense, and high-tech manufacturing. And the more dependent these sectors become, the more urgent the question becomes: how do we secure supply and make recycling more effective? Today, we've explored everything from the origin of the name tungsten to its physical properties and the many ways it's used. We've seen how its exceptional strength, thermal stability, and high density allow it to play critical roles across a wide range of fields. True to its name, heavy stone, tungsten carries real weight, both physically and technologically. But as this rare resource becomes increasingly essential, one question remains: how can we use it more wisely? That may be one of the defining challenges science and technology face in the years ahead. That's it for today. See you next time. This is Dr. Sai Vera Studio.